Hi. So in the previous video, we gone through the industrial IO documentation, kernel documentation. We understood couple of things. What are the different data structure in the industrial IO subsystem? What is buffers? What are the core elements? How the trigger works? What is triggered buffer? And hardware control. So now, based on this theoretical knowledge, we'll go through some actual driver implementation in the Linux kernel, which we can browse and try to understand how these concepts relate to the actual implementation and how the actual implementation comes to. Towards the end of the video, we'll also try to list down the things to something like what are all the things that you need, or what are the core elements of an industrial IO driver, starting from how a module gets registered, what are the different industrial IO APIs, data structure comes to play, what are different functions, how it interacts with the effective bus SPI or I2C, why it gets communicated, and how the actual functionality is implemented. So I will try to note down that as well towards the end. Started. So I have opened the code cross-referencer in Elixir. This is nothing but the latest, most latest kernel code base, 15, and we'll browse one of the IIO driver. Okay, so we'll go to the drivers, open up the IIO. Can go to magnetometer. Okay, so this is a driver for Allegra microsystem LS31300 3D linear hologram. So these are various header files. There are the bits and fields, slip or mslip kind of file for audio. This driver would be utilizing I2C .h, egmap. This is for power management, power management. This is for power regulators, turn on off the powers of sensor. There are generic types and fields. These are the files as IIO. Now we'll jump to the entry point of the driver. This the module init. So here we register the driver using module I2C driver, providing this data structure, which is filled with the driver's details. It's table based on which the compatible matched and driver will be propped, corresponding prop function and ID table I2C. It supports 3 different kind of variants of the driver. So they have defined 3 different compatible field, and each is having their own specific data based on the variant differentiation. Similarly, this I2C device ID. So this will be the entry point. Will register this I2C driver system first, and when there is a device gets found, either by providing it device tree or getting added as a runtime, this driver's probe function will get called. So somewhere up here, okay, we will reach to this probe function. The probe function, now if you pay attention to this thing, and the core elements, they have defined there are 4 elements. The first core element is the IIO dev data structure, and then there is a device allocation, then the device register. This path is for reallocating and freeing the IIO device. We can see here we have defined an IIO dev. Okay, we are using a device managed type of IIO device allocate function. Here we are giving the location data based on the size of the data. The driver specific data structure particular they have defined. So this is DevM variant of IIO device allocate, where they have provided the device structure and the driver specific data size they are assigning into IIO dev. If it could not allocate, it errors out with the OMM. And it gets the private data of IIO dev into data, which is a driver specific data structure. Then they assigns the dev node, which came as a input to this probe function and dev device, sending it to driver specific data and some client data, like there is a mutex type of variable private data structure. There is a struct device type, there is one mutex, they are taking it as protects power on and off the device and access the hardware. So they want to make sure that the hardware, whenever the hardware registers get accessed, it has to be an exclusive locked by this mutex. There is some structure for variant info, contains a single member state for the sensitivity, and there is a reg map, struct reg map as a part of this private data set. We go to the probe function here. They are initializing the mutex, then they are getting the I2C data to get the variant info. Basically, based on the type of variant, they want to get the data that they have assigned here, want to read this thing. So they are using this API to get match data according to that, because the data which they have put is type of variant info only, so catch it as a data or it there. Then that comes the reg map. So they are initializing the reg map over the I2C, because this sensor is connected over the I2C. Provide then I2C client as a put and a reg map configuration. We will look at this configuration holds, and but yeah, this is what using the reg map. Then they are doing some getting the VCC, which is one of the regulator, maybe they have defined in the device tree or somewhere. They get it and they try to enable it. So this is majorly to do with the power on or changing the state power regulator for them. Then comes the industrial IIO dev specific information storage. They are putting an info, assigning to info, they are setting the mode as a direct, they are assigning a name, whatever is there in the I2C name, edit the channels, and then comes the size of the channels and the scan mask. So we'll go through each of this item and try to understand what they define in each. So from the perspective of IIO dev, so we have defined and pointed to the IIO dev, we have allocated it, and now we have reached to adding more information to this data structure. So they have first added the dev info, ALS 311 info, assigning to industrial IIO dev info now. Check what it is. Okay, so basically this info data structure holds what all APIs that you want to use when you access the IIO device. This defines only one API, one callback basically for read row. So whenever you try to read a IIO dev file in the this sysfs, whenever read operation comes, this API will get called. This would be defining basically to how to retrieve the data from the sensor and how to provide it to the user space. As taking as a industrial IIO as a dev, there is a channel spec data structure, the input, 2 references parsed for well and well2, and there is a long mask. Here they are getting the IIO data. So basically they are getting the driver specific data structure hold here, defining so basically a magnetometer holds 4 type of data. This particular magnetometer is XYZ coordinates for magnetic fields and the temperature data. The type of the data for each thing is that this is signed 16-bit and this is unsigned 16-bit. Now mask came as an input to this function, and this will define what type of file was getting accessed from this surface within this IIO dev. So if it is a file node name called processed or raw, it will lend to this particular block. And here, since we are reading the raw file, this will be passed. Here they are calling a function driver get measures. This will be probably taking care of reading the data from the sensor. So they are passing the references to temperature XYZ and the data as well, data that came it as a private data. Go to this one. The whole measure is split into what they are doing. They are from this data they have retrieved the mutex and part of it. They have done some power management. Then they have done some API. Okay, so this is an regmap API. Basically, it does thing like a loop until the data is valued. So they are trying to read the data from the regmap over the I2C and wants to be there until the correct data is there. So not go in detail regmaps thing to this, but this is a blocking call. Basically it is trying to read from the sensor over the I2C and waits for a proper data. Once it is came out of this function, they will check whether it was a timeout. If it timeout, directly error out, return. If it was failed due to this regmap bulk that they have provided here, they also error out with some error. But if it was successful, that means we received the correct data from the sensor. They will use this macro to parse the data that was read and derive a particular value. So they are using this macro to get the temperature data, this macro for X value of this magnetic field, Y value of the magnetic field, and Z value of the magnetic field. They are storing it to the references which was passed to this function. Once it is stored here, they are doing again some power manager stuff and returning from the function. We are again here. We have value read from the sensor as a temperature X, Y, and Z, and based on that we are filling the values to function which we got while we are filling the data. For temperature we have kept T, for XYZ according to XYZ, and we are returning the type as what is the value that we have filled. It's a IIO value integer, so that we for any other address to be passed, they are returning as a the value. If we are trying to read the scale file from the IIO dev, right, then it only gets here in this particular block. They are checking what is the channel type. It is IIO temperature. It provides this value. Looks like this is the calculation that needs to be done to derive the value of temperature from this T. Provide this is the T they want to say. Temperature value is encoded like this: 1000 means T02 is here, and value into -1708. This will be set as an offset in this here. So there are basically in the read row there can be 3 different type of value, 3 different type of file which can be read. Either it can be processed file if we have exposed, either it can be raw file or a scale file or an offset file. Based on what type of file we are reading, this each case gets executed. For raw value we read the actual values of the sensor and return. For scale, the value each value that we have read, whether magnetic field value or temperature value, needs to be calculated with a given equation based on the data sheet. So that scaling factor has to be provided here. It looks like it needs 2 values to be derived from this. They are filling two values, well and well 2, and they are giving, if you look at the return type, they are saying it's a fractional. That means this value well 1 will be the top, and this will go as the dividing factor. If that is only for temperature scaling. What about magnetic? For magnetic, it's simple that it's just a 1 by something. So what, well 1 they have given 1, and based on the sensitivity, whatever we have type, that goes to as a denominator of this fraction. So 1 by this sensitivity, that gets multiplied to the sensor value which we have stored in x, y and z. Then come the offset. So as per this equation, the actual temperature value has to be offsetted with minus 1708. So that they are providing as a minus 1708. And I think offset is only supported for the IIO temperature channel, not for the magnetic channel. Now where did we define it, that which type of value should be there for each channel, is within the this when we define the channel, that comes here. So this is basically the total channel supported by these drivers. This we have provided provided when we are setting the channel. So info we got to know. Info is how you want to basically callback we register on what all operation is supported by this IIO devices within that series of IIO device. This is the mode, what type of mode this IIO device supports. So this supports the industrial IIO direct mode. Basically you can directly read and write from the entries which are there in this system. This is the name of the device, and then the channels. So channel we have somewhat referred in the info, but actual channel is defined here, which is nothing but what all data is supported by this sensor and how it should be passed or what it contains. So now if you look at the documentation, we had something called a IIO channel spec, where we used to define what type of channel it is, how do you want to differentiate it, what all things has to be there, right? So this is a type of temperature, what type of entries it should create for temperature. One is a read raw file entry, one for scale and one for offset. Address means where does it lie into the return data, that when for example buffer scanning is happening, right, you are sending all this data, all XYZ and temperature data as a single buffer. Where does it lie? It lies somewhere here in the temperature. So look at the data channel. It's the first channel, basically call it as a scan index. So address and scan index is 00. Scan type means for a particular end data of a temperature, how it should be treated, how it should be passed. So it gives the idea that whether it's assigned or unsigned. IIO means it's unsigned. What are the number of total bits? So it's a 16-bit wide, and it's stored into the 16-bit value only. Now it could also be possible that for let's say we'll go to that in the magnetic field. I know there. Okay, and NADS is whatever the CPU is architecture is. This is the first channel for the temperature. Next three are for the XYZ. So they have defined a macro so that it does not need to be repetitive code. So that for each channel they are specifying what value to be used and where does it lie. So it's X for X is X, Y for X is Y, Z for Z. It takes as an argument. They are defining type as a magnetic, modified. Channels 2 means IIO mode, what axis is to be there, and what all separate files to be created. Here we saw that it's creating raw file, scale file and offset. Here it's just raw and scale. It does not support offset, it does not require offset, basically maybe based on the data sheet. What is the address and scan index? That we have already seen, like how does it look in the buffer. So when it's XYZ, like first the temperature, then X, and then Y, and then Z. Then comes the scan type. So it's actually signed value which is 12-bit long, but it's stored in the 16-bit. Okay, so stored means what is the variable that you are using. We are using a 16-bit variable, but the actual data is in the 12 bits only, rest 4 are not to be used. Ingredients again, whatever is CPU is following. So this is basically what all channels your driver supports and what all file for each channel will be created and how the data should be passed. This is basically, if you understand, this is the backbone of this entire IIO device. We have got the data, but how user space should interact with this IIO device, that defines on this channel spec. So from this we now have the kind of info, basically holds the callback of how to read the data and how to provide it to the user space when the user space tries to read it. Channels is specifying what all specification this IO device is having, what all channels are there, what all type of data it exposes, and how the data it should be treated. And the scan mask, so scan mask basically, so it's about what when you do read the data, what all channels data will be provided into that. So it uses gen mask 03. So we'll understand what does it 0, 3 and 0 means and what does it called maybe in this stage, but this is what it, okay. Here we have n mask, this is number of channels based on the array size. Now here we are registering the triggered buffer setup basically. That means we support a direct read, but it also support a triggered buffer. That means whenever there is a trigger from the sensor or timer or anyway, basically a trigger is there, the buffer, this driver will read the data and provide the entire data to the user space as a buffer. So this is basically a triggered buffer setup for this. So what it takes an actual device structure, the industrial IO, this is the poll function store time basically, and this is a generic function provided by IIO which just notes down the timestamp of the function. When does the trigger happened, the timestamp of that gets held by this. If you have your own, so basically you are specifying your registering an IRQ as well as top off and bottom off. Is IRQ, top off, and so this is your top off and this is the bottom off. So if you have a specific top off for your need in your driver, you can define your own, but I think this driver does not need other than holding the timestamp. They are using the generic API provided by the IIO subsystem to just store the time of poll function whenever this trigger happened. Then the trigger handler, basically this is a bottom half of this triggered buffer setup, which gets executed after this storing this timestamp whenever trigger occurs. So when the trigger occurs, first top up will be called, where it will since it's IIO specific internal function which store the trigger timestamp, and then it triggers this function to be called, which is the bottom half of the trigger interrupt. So here you go ahead, you come to the stage when the trigger comes. Here you are doing takes an IRQ and void pointer. From the void pointer they are deriving some poll function. From the IIO device they have derived the data. Now they have defined a scan channel. Basically scan channel is nothing but the what data we want to give it to buffer, right? We want to give a temperature value, 3 axis value and a timestamp. Okay, so we first define this signed integer xyz and then temperature for unsigned integer 16 and return value. We use the same API that we used in the row read to read the data, right? Remember, the same function is used here when we read the row value, and whenever we are having the trigger buffer also we are using the same API. So it uses the same method of retrieving the data from the sensor. It stores it into the specific variable T for temperature and XYZ for magnetic fields, and then they create a scan buffer here defined for scan temperature. They fill temperature value, X, Y and Z value for channels, and they provide the timestamp. This they use the IIO API to push this entire buffer with timestamp to the user space as a scan channel. So they are using this industrial IO dev data structure, the scan structure which holds all the value, and the timestamp which we receive from the as a IIO poll function API. Once that is done, we give the trigger notify done, which means the data is ready to be read in the buffer and IRQ is handled. So you return from the IRQ when the trigger came. So this does that. I don't think they would have defined anything for the setup ops. Correct, it's empty. So they don't want to do any setup for the buffer operations because they might not need anything. It's just an empty buffer provided here. And here this is not like you are simply basically registering a trigger buffer. There is nothing that trigger will come or something until you actually register the IIO device to the IIO framework. So everything is just initialization or setting up the stuff. Now here you are setting runtime active, power management stuff here. Again, suspend and resume stuff for what it is needed for, but this you can see it's a PM ops only. Here now this is the final stage where you are registering your industrial IIO device with the IIO framework, IIO subsystem here. Here you give the device structure and industrial IIO dev, which you have filled here. Okay. From now on, your industrial IIO device is available to the subsystem, and you can see the entries in the sysfs. From here on, your user space application read and access this sensor over the IIO subsystem. Whether you register a external trigger based on this, or you directly read the values as a row from the sysfs entries. Now your device will be available to the user space post this API. So yeah, this is it. Pretty straightforward. I'm just going through to understand missed anything. Okay, so this let's see where. So this is basically registers based on the sensor data sheet. They would have defined which value is stored in which particular register that is specific to sensor. So these are all the addresses of that sensor. These are the macros that we talked about. So when the data is read from the sensor over the I2C, how to retrieve a particular value. To retrieve the X value, what do? You process the data like this. So buffer 0, you shift it by 4. Then in buffer 1, you have the again 11 bits again. Then so this basically forms your X data out of that register value read from the I2C. Similarly for Y, this for Z, and this is for the temperature. So this is a repetitive stuff. So they have defined the macros for it, and those are used here when you do the measures. It is straightforward. Cool. So I think what we take from here is that first thing first, you register a driver based on your type of interface it is. Since it's using I2C, we do register an I2C driver with its compatible fields, match table, and probe function. The driver registration part. When there is a corresponding device found, a probe function will be called. Probe function defines three major things. First is the IIO specific data. So there is a data structure and device allocation for IIO. This stuff is specific to this particular device because they are handling the custom stuff. Then so you allocate the IIO device, then you set the data for IIO device. Here in this particular block we are setting everything, how to read the callbacks for read, row, and everything, what is the mode, type, channels, available scan mask, trigger buffer, and then you do the registration of this IIO device to the IIO subsystem. This is three different stages of the registering the IIO device in the probe function. From now onwards, everything will happen based on event based. So either your trigger comes or you manually read the data from the raw files, right? Will be based on the event. So if you do a raw read, your callback will be coming here and read raw, and you will lie to this particular API, and this will process the data. So this will go to the sensor, read the values based on the register reg map, and it will parse it and provide you as a return value of this function, read row. If your trigger gets registered and for every trigger you reach here to this handler, where you do the same thing. You read the data from the sensor and give it to the user space from wherever the trigger came, and notify it that the trigger is completed. Don't forget this part. This is the backbone of this thing, specifying the channel spec, what all channels are supported, and how to treat the data, what all data is there, and how to scale it, what are different types of endpoints this is provided on this interface. It has a raw file, scan and scale and offset, but this is what it. From the previous video we had this one open point, that how does IIO gets connected to, or IIO subsystem gets interface to hardware communication protocol IT specific. As we looked at the driver code, there is no direct I2C or SPI bifurcation in terms of registering with IIO. When we register the driver, we register based on the protocol subsystem it belongs to, whether it's SPI or I2C. It's I2C, so we are registering it as a I2C driver. Within the probe function, we are actually using the IIO irrespective of specifying the communication protocol. Communication protocol only matters for the reg map, because here reg map takes care of communicating with the actual sensor. So here when we are initializing the reg map, we are specifying we want to initialize the reg map with I2C. So here whenever reg map goes ahead and try to read the sensor data, it uses the I2C as a communication. But for IIO there is no direct correlation with IIO. Now let's note down what are the elements that we have figured out from the driver, that how does IIO driver IIO device is structured. Basically first part is module registration, so the driver registration. This is based on whether it's I2C or SPI. We define driver for it, for which we have given the structure, whether it's I2C driver structure or SPI driver, right? And we use it to register using module register, like that. From there we provide all the compatible fields and probe function, basically from which the device specific entry will happen, right? So this defines that compatible and probe part, compatible. From here, when the probe for a particular IIO sensor device gets invoked, we will reach to this probe for this device, which covers four major things related to IIO. First is the declaration of IIO dev, defined with in declaration. We define that there is a IIO dev to be used. Okay. Then we allocate the IIO dev using the IIO dev APIs. Then we actually sets up the various IIO dev specific members. What are those? Those are the channel spec, main thing, right? What all channels which will be proposed and given to user space. Is IIO info for specifying the callbacks for row read, row write. Then we do the triggered buffer registration, right? Because we want to provide the triggered buffer data support to. And a lot other things like modes and name. There are trivial things as well. This is the sets up those things. Then comes the actually registering the IIO dev. From here on, your driver will be available to the system as IIO dev and all these user space applications. Now once it is available to the system, there can be two entry points to this using the data of driver. One is the triggered buffer. Whenever there is a trigger, right, your driver will invoke its handler, invoke the handler for triggered buffer, which will, what it will do basically, it will read the data from sensor and pack it in buffer and sends out to user space, right? This will be a all data, bulk data in bulk, all what all channels are supported by your driver, all data will be there. Then there is other way, which is direct read, that direct raw read or write. Here you will have a channel specific files, right, which is created under the sysfs, where you read the data, then your raw read basically get called. From here you do the same thing, read data from sensor and return basically the channel for which we have requested the data, channel specific values. Here the thing needs to be noted here is this will be a channel specific data, whereas in the buffer triggered you will have all the channels combined in a buffer and sends out. Then comes the main how the data retrieval takes care, because in this driver which we have looked, it had RegMap implemented, which means all the sensor communication, sensor specific communication over the any protocol. Here it was I2C, but or SPI could also be there, will be taken care by the RegMap. So these are major components by which an IIO driver is structured and works. In the next video we will cover RegMap. So this was all. Thank you for watching.